Hi all, welcome to the third part of the video lecture on complexity theory. So here we will quickly go through the deterministic versus non-deterministic algorithm, and we will formally define what is class P and NB problems. Okay, so in the previous two video lectures we covered the basic concept about hard as well as easy problem and different aspects of the same. Okay, and also we saw what is optimization problem, how it is different from decision problem, and how we can solve an optimization problem by asking series of decision problem. So now onwards, in our subsequent discussion, so whenever we are considering problem, mostly we will consider decision problem. Okay, so optimization problem is something that you can solve by asking series of decision questions, right? So we will basically consider decision problem, and we will classify them into different complexity classes, and that you can generalize to optimization problem also. So that is the way we will be approaching problem. So now here let's quickly go through what is deterministic versus non-deterministic algorithm. So this is something like NFA and DFA, like deterministic automata and non-deterministic automata, NPDA, DPDA, those things you studied in your automata theory, and you know what is determinism and what is non-determinism, right? Now we will see that similar approach in algorithms also. So what do you mean by a deterministic algorithm? Every step of the computation is uniquely determined, means as part of the algorithm each and every step is uniquely determined. So after executing a particular step you clearly know where to go next, right? So here there is no guessing at all. So for example, if you are looking at the searching procedure, the typical searching procedure that you are familiar so far is deterministic in nature. So for example, your linear search, so what you will be doing, even though it is binary search also, that is the type of algorithm which you are knowing is deterministic, because every step is very clear, straightforward, and without any guessing. Okay, so if it is a linear search procedure, how it will proceed? First it will check whether this element to be searched, say x, is matching with the first element of the array. Say check if a of on equal to x. If yes, we will answer it as S element found. Otherwise, the next step is very clear. Just go to the next element of the array, that is A of 2, and check whether it is equivalent to x. If that is not the case, the next step is very clear. Go to the third element of the array and check whether it is equal to the element to be searched, x, right? So like that you will go up to the last element of the array, and this will be proceeding in a systematic way, right? So this is what we call it as a determinism, right? So everything is very clearly defined without any guessing. You can in a straightforward manner you can proceed from one step to another, like that. And you can see that the typical searching like this will take a order of n complexity in the worst case. For example, the element is present at the end of the array or it is not there in the array. In both cases you have to do some n number of searches if I have an array with n elements. Okay, so I have an order of n deterministic algorithm, and this order of n is a polynomial running time also, right? So I can say that this particular deterministic searching or the type of linear search algorithm we gone through is having an order of n deterministic poly time solution, running time, like that. Now the same problem, the searching itself, we can consider the non-deterministic version, and here you can see that it is something, it is trying to proceed in a parallel way. So typically non-determinism, there are multiple ways, and each way will be guessing out some possibility towards a solution, right? Like our NFA. So how we can approach our searching in a non-deterministic way is one person will be guessing or trying to see whether the first element of the array is matching with the element to be searched, that is x. At the same time, parallelly, another person will be checking whether a of 2 is equal to x. At the same time, third one will be checking a of 3 is equal to x, and now all these people are working together in simultaneously. Okay, so the difference here is in case of deterministic search, the procedure is deterministic or straightforward, or it is proceeding in a step-by-step manner with respect to a single CPU. When it comes to non-deterministic search, say n number of CPUs are working in parallel. If I have an array with n elements, and each CPU is just doing a single comparison, say the first CPU is comparing the first element of the array with x, the element to be searched, and at the same time the second one is parallelly working, and it will check to see whether a of 2 is matching with the x. At the same time, parallelly or simultaneously, the third processor will be checking whether a of 3 is equal to x, like that. So all of them are working together so that actually it will take the comparison of a single element. So whenever you are comparing a single element, actually n processes are doing this comparison on n elements. So all positions of the array is searched simultaneously, right? So the time taken is just order of 1 only, because what is the time taken for a single comparison? Only you have to spend that much time, but you have to utilize a number of resources. Say n processors have to work together to get a order of 1 polynomial time algorithm. So this is order of 1 or order of n, both are polynomial, right? But when it comes to this order of 1 poly algorithm, say searching algorithm, it is non-deterministic in nature, because many people are trying to work together, so or all are guessing different possibility and they are proceeding. Okay, so I can see that for the searching procedure, I am having an order of n time or deterministic algorithm, and at the same time I am having just an order of 1 non-deterministic polytime algorithm. Okay, so see, it is very important. Here it is order of n deterministic polynomial time algorithm, where here it is just order of 1. So both are polynomial only, where it is order of n or order of 1, but here it is deterministic, here it is non-deterministic, and always this constant time is much smaller compared to the I mean linear time like order of n, so that you know. So now let's see as and how we can apply this non-determinism when it comes to sorting. So first let's see the normal deterministic sorting algorithm, which you are familiar, whether selection bubble or some sorting approach. So what we are basically doing is some kind of comparison and swapping together you will be executing, right? So bubble sort, you think about it, we will compare the adjacent element and we will keep on swapping. Selection sort, you will find the minimum, and for finding minimum you will do some comparison and then you will swap with the first element, like that. So basically you can see some comparison and swapping happening in any sorting algorithm, that is also proceeded in a step-by-step systematic deterministic way. So say the first two elements are compared, then swap if needed, then second two elements are compared, then swap is needed. So like that it is proceeding in a step-by-step systematic way, right? Like bubble sort, insertion sort, quick sort, etc. And all these deterministic sorting algorithms, which you are familiar already, is going to proceed going to give you a running time of say order of n square or order of n log n. In bubble sort, insertion sort, these are giving order of n square time in the worst case, where this merge sort, heap sort and all giving order of n log n in the worst case. So anyway n log n is much better. So you can see that the deterministic approaches are taking some n square or n log n time. Now what about the non-deterministic sorting? So how we can proceed this sorting in a non-deterministic way, or how we can utilize the multiple resources, multiple CPU and its time, everything, so that we can do the sorting in a much better time. Say instead of, so now we are having just an order of n non-deterministic polynomial time algorithm possible for sorting. See, order of n is a much smaller running time compared to n square or n log n. So deterministic algorithm, there is no order of n deterministic algorithm available as of now for sorting, and it is not going to be happen in the future also, that we already seen. For sorting algorithm, lower bound theory says that the lower bound is n log n. So you can't improve from n log n in a deterministic way, but you can improve from n log n provided you have this non-determinism with you. So what you can do is just you can think of it in a number of ways. This is one approach. So this is an input given, some set of elements are given and you know how to sort them. So after sorting, this could be the result. Now what these different processes are going to do, say simultaneously at the same time, the first processor will be guessing the correct position of the first element, say -5, whether it is to be occupied at the first position, second position, third position or fourth position. The second processor will be guessing where I can correctly place the element, the next element. Okay, say element 1. So sorry, the next element is 9, right, as per the input. So second processor will be guessing that. So first one will be guessing the correct position of -5, second one will be guessing the correct position of 9, and third one will be guessing the correct position of 1, and fourth one will be guessing the correct position of 4. So this is how the processor will be guessing the correct position of the element. So this is how the processor will be guessing the correct position of the element. So this is how the processor will be guessing the correct position of the element. So this is how the processor will be guessing the correct position of the element. So this is how the processor will be guessing the correct position of the element. So this is how the processor will be guessing the correct position of the element. So this is how the processor will be guessing the correct position of the element. So this is how the processor will be guessing the correct position of the element. So this is how the processor will be guessing the correct position of the element. So this is how the processor will be guessing the correct position of the element. So this is how the processor will be guessing the correct position of the element. So this is how the processor will be guessing the correct position of the element. So this is how the processor will be guessing the correct position of the element. So this is how the processor will be guessing the correct position of the element. So this is how the processor will be guessing the cor 3, right? So like that it is proceeding. Now the interesting thing is like how much time it will take for just guessing the position of a particular element. So this minus 5, if you are looking at minus 5, it can be there in the first, second or third or fourth position. So that correct position you have to guess. So one way to guess it will be like say suppose you are taking the element 3 and you want to find out where this 3 correctly you can place after sorting, right? So you know it is the third position. So after placing 3 in the correct position, you can see that all elements less than 3 are to be placed at the left side of the array, and all elements greater than 3 should be at the right side of this 3. So you can just count the elements which are less than this 3 and you can see whether that many places are left before this 3. Okay, so something like that. So here in our example you can see minus 5 and 1 are less than 3. So the correct position of 3 will be 2 places after the from the beginning. After 2 places from the beginning, because first 2 places will be occupied by the elements less than 3, that is minus 5 and 1. Then 3 will occupy its place, and after that the element greater than 3, that is 9, will occupy the fourth position. So like that you can guess, and this guessing is going to take some order of n time only, right? So this is what is happening, order of n time. Non-deterministic algorithm in the sense each processor will be guessing a position of a particular element, and thus that particular guessing is going to take some order of n comparisons, because you have to guess whether this particular element is at any of the places from 1 to n. Okay, so that guessing is going to take some order of n time. And all the n processors, so here I have an array with n elements and I am using some n processors also. Everybody will be doing this searching simultaneously, and each one will be guessing the position of a particular element, and everybody will be finishing at the end, and finally you have the sorted array, right? Maybe in a global array they may be updating like that. If that is the case, you know, order of n time only we are spending actually, but resources we are utilizing more, and we are getting the elements sorted in order of n, non-deterministic time, non-deterministic polynomial time. Okay, and on third use case is like, so first we discuss about the deterministic and non-deterministic searching, hope it is clear. Then deterministic and non-deterministic sorting. Now it's time to see a difficult problem, say traveling salesperson problem, which you already know. It is going to have a so the trivial approach, the deterministic approach you already know. So one trivial way is like a try all possibility. If there are n cities to be visited by the traveling salesperson, n cities say represented by n vertices of the graph, you can arrange it in n factorial ways. So any one of them is going to be at minimum TSP tour. And sometimes it may be the case that no minimum TSP tour exists also. So whatever it is, you have to explore some n factorial arrangement. So the time taken will be order of n factorial, and from that we have a reduction by applying that branch and bound technique. So that will reduce this n factorial to 20 power n and 2 power n. And then further there is a reduction to 2 power n. Now we already seen that shall we improve from this 2 power n? No. So that is already proved by that lower bound theory. So that also we didn't see the theorem. But we know that proof is available there. So this is a deterministic TSP. So the deterministic way, in a straightforward way, how we can proceed the problem. Now you can think about the same problem in a non-deterministic way, say something like this. So it is what is happening here. So first you are going to visit the first vertex, say v1, whatever it is, you can choose some vertex and visit it, and simultaneously in the next step, right, you are going proceeding in a non-deterministic way, like, so following v1, shall I try v2 or shall I try v3 or shall I try vn? So 3 processes will be taking in charge, and first one will see whether the path, say v1, v2, and from that point is it feasible, and second one will be checking whether the path, say v1, v3, from that point is it feasible, like that. So at this point you can introduce 3 processors. Already one is there, it can choose one of the path. 2 more processors you can introduce. Now at the next step, if you want, you can further add parallelism, say so right now our path is like a v1, v2, then we can go to either v3 or some other vertices other than this v1 and v2. So that many possibility. At that point, if you want, you can introduce more processors. So like that you can proceed. So all together, say in the worst case, what is happening is see how many paths are possible, right? So each path is being tested by a particular processor, like that you can expand. So in the to get the best performance, if you say if you are having n factorial processors with you, and each processor is going to explore a particular permutation, say v1 v2 v3, is it a feasible TSP tour, or first of all, is it a feasible Hamiltonian cycle? If it is a Hamiltonian cycle, then you can find all Hamiltonian cycle, and you can find out the one with the minimum weight. That will be your minimum TSP tour. Anyway, you have to explore all n factorial paths, right, in a trivial way. Now we are depending on n factorial processors to do this thing in a parallel way. Now what is the time taken by a particular process? It just has to verify, so that verification is important. So it just has to verify whether a particular sequence of vertices, permutation of vertices, say v1 v2 v3 etc to vn, is a valid Hamiltonian cycle or not. If that is the case, is it minimum, that checking will go parallelly. So the verification is just going to take some order of n time, right? Because I have a sequence of n vertices, I have to see whether it is a Hamiltonian cycle, means whether it is going to anyway it is going to contain all vertices without any repetition. So you just have to verify whether it is a valid path or not. Is there any edge exists from v1 to v2, then v2 to v3, like that? If that is the case, I can say that it is a Hamiltonian path, and if it is going back to the starting vertex, Hamiltonian cycle. So basically TSP tour also we are trying to find out this Hamiltonian cycle, which is of minimum weight. So that minimum finding you have to run further. Okay, anyway you got it, right? So we are depending on some n factor processes, all are working parallelly, say in a non-deterministic way, so that you can wind up this entire searching in the sense the process of finding a TSP tour in order of n time, which is a verification time. So the thing is that even though you are applying non-determinism in the sense parallelly, simultaneously many processes are working, the effort spent by a processor should be polynomial. That is very important. That polynomial time verification should happen. Okay. So here it is, that is the case, and accordingly we have a just order of n non-deterministic polynomial time algorithm feasible. Okay. So hope it is clear. This lower bound theory, those things we already come across, right? Yeah, that about it. So the time taken is just order of n, but many n factorial people are working parallelly. That's why you can finish it in order of n time. Now it is very important. Say the deterministic approach is taking some order of n time, where the non-deterministic approach is just taking order of n time. So this is very important. From 2 power n, which is an exponential running time, now we have a reduction to just n, which is polynomial. Okay. If you are looking at the sorting and all, from order of n square, we are having a reduction to n. Both are polynomial only. So polynomial to polynomial. Say in searching also polynomial to polynomial. But when it comes to TSP, we have a reduction that is from exponential to polynomial. So the gap is like the traveling succession problem, the exponential gap is there between non-deterministic and deterministic approach, or in other ways you can see non-determinism is going to save a lot of time, but non-determinism itself is not good in the sense multiple processors, that many resources should work parallelly, so it is not a resource efficient solution. But at the same time, if you are looking at the time complexity part alone, you can see this is just taking order of n time, and how we are achieving it, that is a different story. So that much difference is there, say when it comes to a problem like a TSP. But for normal polynomial algorithm, even after applying non-determinism, you may not get much benefit. But when it comes to a non-deterministic algorithm, non-deterministic in the sense, in the deterministic settings it is taking exponential time, but when I just applied non-determinism for such a problem where the determinism is going to give you exponential time, suddenly the time is being reduced to some polynomial time. So such problems are what we are more interested. But this is not the case with every problem. Sometimes even after applying non-determinism, still the algorithm might take a exponential time. That means the verification alone you can't do in polynomial time. Okay. Yeah. So the question is, can we get a deterministic polynomial with the deterministic settings itself? Can I reduce the 2 power n? That we already seen. It is not possible by lower bound theory. So answer to this question is no. So it is not possible to have a deterministic polynomial time travel in Swain problem. No, in the sense, for the time being, as of now, there is no algorithm exist. Okay, so here I written like a lower bound theory. So here it is actually a question mark. I think in between I explained wrongly, because subset enumeration and all, by lower bound theory we have a proof that there are 2 power n subset for sure. So definitely you can't save time. But can I reduce from this 2 power n? So this is interesting. Sorry, in between I explained a little wrongly. So now just follow me. What I'm trying to say is, right, in the deterministic settings, that is by using a single processor, from n factorial we have a reduction to 20 power n, and from that it is having a reduction to 2 power n. Now the question is, can I reduce from this point? Okay, can I improve time from this point? Or can we get a deterministic polynomial? So this is deterministic exponential algorithm. So can I get a deterministic polynomial time TSP? So it is the solution. I can't say that yes or no. It is just an open problem, I can say. Okay, open problem in the sense, as of now, no one come up with a deterministic polynomial time algorithm for TSP. Deterministic polynomial algorithm. Deterministic polynomial. Okay. I mean, in deterministic settings, no, it is not possible for us to reduce that running time from 2 power n. But in the future, can anyone come up with a better algorithm? That also we don't know. Okay, so there are two ways to approach a problem. Either you show some improvement, say from 2 power n, can I improve in the sense even 1.5 power n, that also an improvement. But the question is, can I improve to some polynomial running time? But you might feel like it is not possible, because so far no algorithm is there. So how can I come up with an efficient algorithm? But don't think like that, because I can just tell you one problem. You can Google about it. Say the KMB algorithm for checking whether the primality testing. So it's not KM. Sorry, it is AKS algorithm. In between I checked it. Okay, so you can Google about it. Okay, so this is for doing primality checking. Okay, so this is three people, Agarwal, Kyle and Saxena from IIT Kanpur. They developed this algorithm for primality checking, which is a polynomial algorithm. So this is something that happened very recently, but before that this was an exponential only exponential solution available for that primality checking. And also at the same time, so there is some algorithm called Miller-Rabin primality test that was popular but before this AKS algorithm. But suddenly when people come up with a solution, so that problem become P. So I mean, is easily solvable, something like that. Okay, so that if you have time you can think about it. So the question is, can I improve from this particular 2 power n? The answer is we don't know. Okay, so for the time being there is no algorithm exist that will improve from this 2 power n, and we don't know whether such an algorithm will come in the future also. So that is the answer. Can we get a deterministic polynomial time algorithm for TSP? The answer is we don't know. You can say that it is not possible provided you have a lower bound theory proof. So that we already seen. For we can say that we can't improve from n log n for sorting. We have a lower bound theory proof. So we can't improve from 2 power n for enumerating all subset kind of problem, because by the inherent nature of the problem says that there are 2 power n subsets. You have to spend some time for each subset. 2 power n will be the running time. You can't improve. But can I improve this 2 power n? When it comes to TSP, the answer is we don't know, because there is no lower bound theory proof available that says that this is the best lower bound. So there is a possibility of reduction, but as of now there is no such better algorithm available, but we don't know the status in the future also. So like that, these problems are what we are interested basically. So accordingly we have the complexity classes class P and NB. So basically what is P? P for polynomial running time. So that is very important. Not only polynomial, deterministic polynomial. So by default when I am saying polynomial running time, I am thinking about a single processor executing my algorithm. So in a deterministic way. So by default class P problems are nothing but deterministic polynomial time algorithm. So that is very important. So both of the terminologies are important. Class P means deterministic polynomial time. So don't say that polynomial, right? Then can you tell me what will be NB? NB, some people are saying like no polynomial time. That is wrong actually. No deterministic polynomial time. Otherwise, the only available algorithm I am having is non-deterministic polynomial time. The second one is more accurate, like okay. So class NB means the problems that have a non-deterministic polynomial time algorithm. So why it is important? Because as I already told you, in the non-deterministic settings itself, sometimes the algorithm might take exponential running time. Say something like a non-deterministic exponential time. I mean that means that verification process itself, I can assign the task to some n factorial number of processors, but still the time taken by a single processor for verifying a particular subpart of the problem, if that itself is taking some exponential time, then it is not in our control even. Okay, non-deterministic exponential running time, that can happen. So what we are interested is, at least in the non-deterministic settings, say when n processes are working together, I should get a polynomial solution. Otherwise such problem I don't have to spend time on it. Okay, so that is inherently difficult. So under class B, most of the algorithms that you studied already are class B. I mean deterministic polynomial time. For example, the searching, sorting algorithms, minimum spanning tree algorithms, the shortest path algorithms, all of them that you studied, say matrician multiplication problem, all are coming under class B. Now what is class NB? That is what we are going to see next. For example, graph 3 coloring, and many of the problems I just given you an overview in the first part of the video lecture. Hope you remember, say checking whether a graph is Hamiltonian or not Hamiltonian, finding Hamiltonian cycle. Okay, and similarly the TSP, graph coloring, satisfiability problem. Okay, so these things, some of them I already defined what it is, and there are many problems like vertex cover, click, matching. So there are many such problems that are coming under NB, and we are more interested to such non-deterministic polynomial time algorithms at this point. So here you can just see how the tree coloring is working. I mean try all three colors for each and every vertex, that kind of an approach that you can just go through. Okay, so this is what we are trying to say so far. So basically we are interested on solvable problem, in the sense there exists an algorithm, some kind of algorithm exists, say after some finite number of steps. That finite may be polynomial or exponential, but still after some finite number of steps the algorithm should terminate. Then only I can call it as a valid algorithm. If for a computational problem such a valid algorithm exists, I can call it as a solvable problem. But there are like a halting problem of a Turing machine and all, they are unsolvable. Okay, that is different category, we are not interested. So right now we are interested on solvable problems only, and there itself what is the time taken to solve the problem, whether it is polynomial time solvable or exponential time solvable. So by default we are talking about deterministic settings. Okay, so in the deterministic settings, whether it is polynomial or when it comes to exponential, by default whether it is deterministic or non-deterministic, it is purely taking exponential running time. And you know examples of polynomial algorithm and exponential time algorithm, like enumerating all subsets of a given set. You know, at 2 power n subsets are there, so with each enumeration you have to spend some constant time, because you have to enumerate everything, right? So it will take a exponential running time for sure, whether in deterministic as well as non-deterministic settings, right? Similarly, enumerating all spanning trees of a given graph or given complete graph, some n power n minus 2 Cayley theorem is there. These are all coming under exponential running times. Now there is a class of problem that are coming in between polynomial and exponential, in the sense we don't know actually their status, whether it will go to exponential time complexity, say in the deterministic settings, or whether it will go to polynomial category, that we don't know. So that's why we are putting them in between, and the speciality is like in a non-deterministic settings these problems are taking just polynomial time, so I can call them as class NB problems. So this left side I have a class P problem. So this is the collection of polynomial time algorithms, otherwise called as a class P problems, and the right side actually we are not interested on that, and if you want you can call it as class exponential something. I'm giving a name like that, but in the most of the textbook they are talking about class P and class NB only, and this is a set of problem coming under class NB. So why they are sitting in between? Because we don't know the status whether they will go this side or that side, so it's an open problem for you. So, can you guess how many such problems are there in when it comes to computation problem? And so somewhere I read like around 5,000 plus problems are being listed under this category, and some are very important and maybe familiar to you. Say finding maximum click of the graph, say complete subgraph, that is click, or minimum vertex cover, maximum independent set, whatever needed that I will explain. So there are many problems. Longest path, shortest path is under class B, where longest path is class NB. Graph coloring, stain a tree, exact cover, Hamiltonian cycle, Eulerian cycle checking is class B, where Hamiltonian cycle checking is class NB. TSP like satisfiability, etc. Satisfiability again I discussed like 2 sat is class B, 3 sat and above. Similarly, graph coloring, 2 coloring is easy, I mean class B, and 3 coloring and above are coming under this category, class NB. Now the next question is whether this set of all problems which are having a polynomial, deterministic polynomial times algorithm, and set of all problems which are having a non-deterministic polynomial time algorithms, both of the sets are equal or not. You may be thinking two different problems we are talking about. One is having deterministic polynomial algorithm, another one is we don't know. that is the answer actually. Whether it will get a deterministic polynomial time algorithm in the future or not, that we don't know. So for the time being it is having a non-deterministic polynomial time solution only. So that is another set. So both are looking like independent, but we are just some people are interested to see whether these two sets are equal or not. Okay, so why this problem is important? Because people started thinking about such an possibility, like in the future all non-deterministic polynomial time algorithms are going to get a polynomial solution. But it may or may not happen, but this is something very interesting when it comes to this theoretical computer science. Okay, and why it is important, and what is happening, why what is the real reason behind this kind of a question, that we will see soon, maybe in the next video lecture. So right now let me just ask you whether this P and NB is same or not. But the obvious answer is it is not same. That is the intuition we are getting, but actually as of now our current belief is also like that it is not equal, but it may change in the future like that. Some people are believing like a P and NB are same. But just like our intuition, most of the people are thinking like so that is the current belief also. P is not equal to NB, but there are certain people who are arguing like a P can be NB in the future, so we don't know. So basically, even though I can just say that P not equal to NB is our belief, the problem is nobody is able to prove that belief. Okay, so as soon as there is no proof available, I can't accept that belief. So that is the thing. Say whether every problem in class NB has a deterministic polynomial time algorithm or not. That is what we are interested. And our current belief is P and NB are different and P is a subset of NB. Okay, so why it is a subset in the sense, for every P problem you can think about an NB solution also. For example, searching, sorting, these are P, but that's searching or sorting itself you can done in a non-deterministic polynomial time way also. We already seen for searching, sorting everywhere, non-deterministic as well as a deterministic approaches we saw. But when it comes to certain problem like a TSP and all, there is only non-deterministic polynomial time solution available, and there is no deterministic polynomial time algorithm possible. So that makes this P a subset of NB. NB is something, a superset, which is say going to contain some problems like this, say max click, minimum vertex cover, maximum independent set, etc. And it is a superset in the sense we don't have a polynomial solution for them. But for most of the P problem we can think of an NB version also. So that is why it is getting a it is looking like a subset. Okay, so that is our belief, but we don't have a proof saying that P is a subset of NB. It is just a belief. Nobody is able to prove this mathematically. So as long as there is no proof, this is just a belief. Nobody is going to accept your belief, something like that. And still there is a chance that people can argue that this is not the correct correct in the sense P and NB are just some equal set. So whatever be the problem in P and NB, both are same, or in other ways, for every NB problem I have a polynomial solution also. I can have a polynomial solution also. So like that. So altogether it is something listed as the so what I can say, like the resolution to this issue, like whether P versus NB, whether both are equal or not equal. If it is our belief is correct, we should be able to prove it at least. If we are not able to prove it, can we say like a P equal to NB? So anyway, this is just a question mark or open problem, and not only this, there are many such problems in theoretical computer science which are open, in the sense nobody is able to come up with a correct answer for that. Okay, so for the time being, so if someone is able to resolve this problem, even you can also try it maybe in the future. So definitely you are going to get some $1 million. So like that, the Clay Mathematical Institute is offering you a prize money of $1 million for the resolution of the P versus NB question, and it is the first of 7 such problem. I mean, not only this, there are 7 or more than such similar problems are available when it comes to theoretical computer science, and this is one of the problem that we are going through. So that about it. Hope we get a feel about it, and what is the intuition behind this kind of a question and all, we will see, and how this P and NB, if you if you want to prove, say in the future, this P and NB are equal, one simple thing that will so ask, what is your intuition says. The only thing is like take each NB problem and come up with a polynomial solution. If you are able to do that in the future, so every NB problem you are taking and you are trying for a polynomial algorithm, and you are succeeding with that, you can definitely say that P equal to NB. But see, think about this difficulty. There are 5,000 plus problem. Everyone, there is no relation with each other. Simply you have to treat every problem independently, and you have to pick each one, and you have to see whether it is going to give you a polynomial solution or not. So it is not going to work actually. Okay, so shall we do this checking in an easy way? Actually, as long as such a problem is relevant, there should be some way, right? Some trick will be there. So how we can, if you want how you can prove that P equal to NB, there is a trick actually that I will tell you. Say I will try to cover in the next video. So hope you are with me so far. Yeah, thanks for listening.